how to improve inrush current protection using NTC base limiting and PTC base limiting. This presentation will focus on the following topics: what is inrush current, managing inrush current, NTC base limiting, PTC base limiting, and NTC versus PTC comparison. Let's get started. First, let's define inrush current. As shown in the graph to the right, inrush current describes a spike in current that occurs when equipment is powered on. Next, let's discuss managing inrush current. Inrush current can be properly managed through either NTC or PTC limiting. If inrush current is allowed to pass through the system, it can reduce the effective operating life or even damage equipment. Let's look at an example. As you can see in the photo here, an NTC thermistor has been embedded for inrush current protection. Without this thermistor, an uncontrolled flow of inrush current can damage the diode bridge and link capacitor, disabling the conversion of AC to DC current. This can lead to system failure. Managing inrush current becomes further complicated for systems that switch on and off quickly. This is because the limiter must reset instantaneously to protect the system. Later, we will cover how to address this using a PTC thermistor. What is NTC base limiting? NTC stands for negative temperature coefficient. The NTC thermistor provides variable resistance based on temperature. As temperature increases, the resistance drops from high to low and allows current to pass through. NTC thermistors are the most commonly used thermistor. They fit a wide range of applications, including automotive, military, industrial, and emissions controls. Various everyday items contain NTC thermistors. A few examples include HVAC motors, audio amplifiers, MRI machines, X-ray machines used for airport security, motor drives, which can be found in treadmills, and also PC power supply. How does NTC base limiting work? To limit inrush current, an NTC thermistor is placed between the power supply and system as shown in the figure to the left. Upon power on, the NTC thermistor provides high resistance to limit inrush current. As the inrush current drops, the NTC thermistor self-heats and its resistance drops to a low enough value to pass current through. Let's look at another example. Consider a system with 10 amp continuous current, an inrush current of 100 amp, and an input voltage of 240 VAC. Upon power on, an NTC MS32-10015 thermistor has an initial resistance of 10 ohms. Now, consider the worst case scenario of turning on the system at peak voltage. This will result in a peak voltage value of 340 volts. Instead of passing 100 amp, the NTC MS32-10015 only allows 34 amp to pass through. As the NTC MS32-10015 self-heats, its resistance drops and the current lowers until the inrush current stops completely. The NTC MS32-10015 still continues to heat, dropping resistance to as low as 0.07 ohm, where it then reaches a steady state and passes current through with a minimum loss of efficiency. NTC base limiting has several advantages. First, it occupies only half the board space compared to a fixed resistor. Second, it has a very simple selection criteria to design in the circuit. Next, it also requires no bypass circuit because resistance drops as it self-heats. And lastly, it costs less compared to a limiting fixed resistor. In fact, NTC base limiting is the most cost-effective way to limit inrush current. What is PTC base limiting? PTC stands for positive temperature coefficient. The PTC thermistor also provides variable resistance based on temperature. As temperature rises, resistance increases from low to high and blocks inrush current. Typically, NTC base limiting is used for most applications. However, there are certain scenarios where PTC thermistors are the optimal choice. When should PTC base limiting be used? A PTC thermistor should be used when ambient temperature is greater than 65 degrees Celsius, ambient temperature is less than 0 degrees Celsius, reset time needs to be near 0 second, or to prevent a short circuit. How does PTC-based limiting work? A PTC-based limiting circuit requires a bypass circuit to send current back through the PTC thermistor to protect the system against shorts. By setting the bypass to 3 or 4 times the amount of time it takes for the inrush current to settle, response time for the PTC-based limiter is extremely fast. Let's take a further look at PTC-based limiting. Referring to the graph to the right, resistance for an NTC MS3210015 thermistor drops as it self-heats, while resistance increases for a PTC MCL20500100 thermistor. At a specific threshold of 120 degrees Celsius for the PTC MCL20500100, resistance increases sharply, enabling the PTC MCL20500100 to respond quickly to inrush current. Also note how the PTC MCL20500100 has a flat rate response at low temperatures, making it effective across the entire temperature spectrum. PTC thermistors have a few trade-offs. 1. They cost 1.5 times more than an NTC thermistor. 2. They also require an active circuit to bypass the PTC thermistor. However, the increased responsiveness and advanced protection outweigh these trade-offs. In conclusion, an NTC inrush current limiter is commonly used in a wide variety of equipment and applications. At high temperatures, its resistance is low. On the other hand, a PTC inrush current limiter is used in specific scenarios, such as extreme temperature conditions, near-zero reset time, and to prevent short circuits. At high temperatures, its resistance is high. Thank you for joining Amatherm for today's presentation on improving inrush current protection. For questions or to request a sample, please visit our website at www.amatherm.com.